Here's the sampling situation as we've set it up. We have a population of individuals whom we know the IQ scores of. It has a mean of 100 and a standard deviation of 15. We applied treatment to just 16 of these individuals and measured those individuals on their IQ after treatment. Now, although this is the way we would actually do this experiment, it's statistically analogous to another situation and one that we always need to retain in the back of our minds when we're doing science. What we're really making an inference about is a population that's been treated. What would happen if every individual in the population were to take our treatment? What would the population mean be after that treatment? So let's draw in a hypothetical situation on the right. Remember, this isn't ever how we would do science, but this is what we are trying to make an inference about. So instead of treating our sample, instead, we're going to take everyone in the population, whom we're assuming are not taking ginseng yet, and apply a treatment to every single one of them. If we were to measure that population afterwards on IQ, we would have a population of treated individuals for every individual. So by the method of difference, the only thing that differed between these populations would be that ginseng treatment, and any change in this population to the mean would give us an idea about the exact effect of ginseng. Notice that for populations, there's no sampling error. If we treated everyone and measured everyone, there's nothing else that could be accounting for a difference other than ginseng. Now, before I go on, I want to mention one important assumption we'll make. We're talking about treatment effects on the mean, so we're going to be interested in that population mean after treatment. To simplify things, we're going to assume that ginseng does not change the standard deviation of this population, so the only way this treatment will have effect will be on the mean. So that's what we're interested in characterizing, the mean of that population after treatment. Now, like always, we can't measure entire populations, but we could take a sample from this treated population, a sample of size 16, and then measure their IQ scores. So notice how analogous these are. We can either take a sample and then apply a treatment and measure those individuals, or apply a treatment to an entire population and then take a sample. In essence, those are the same things. So, our sample mean is actually an estimate of this treated population, the population that would exist if we were to treat everybody in the population. So our statistical hypotheses are about those two populations as if we had made them. But notice in science, we never treat an entire population, but implicit in our hypotheses is that that is what we are trying to estimate, the difference between the population before treatment and this population as if we had treated everybody. So statistical hypotheses are always about population parameters, not about samples. Samples can have sampling error. If our hypotheses were stated as X bar for treatment is not equal to or equal to X bar with treatment, that makes no specific claim. Sample statistics can always differ due to sampling errors. If we're actually measuring a population, they can only differ due to the treatment. There's never sampling error for population parameters. So that's what we're interested in characterizing. So going forward, if we look at that population after treatment, the null hypothesis is going to make a very specific claim that that mean after treatment is exactly the same as the population mean before treatment. Now, it can't be any different for the null to be true. If that population mean after treatment is 100.00001, that is still implying or is still saying that the null hypothesis is false. So notice that the null makes a very specific claim about that population after treatment. In this context, that the mean of a population treated with ginseng would be exactly 100, and the alternative hypothesis simply states that the mean after treatment is not equal to 100. So these are our statistical hypotheses. The null hypothesis, the special hypothesis in science that simply states whatever we measure in our sample, if it's different from the population, it's simply due to sampling error alone. And the alternative hypothesis, which states that the difference we observed is due to sampling error plus some true effect. And remember, our job here is to discredit the null hypothesis.